Hello everyone. So in this lecture 4 of semigroup theory, we are going to study about zero groups and subsemigroups. So we have to recall some notations from the previous lecture. We can see that when you have two subsets from a semigroup, um, namely A and B, then the product of two sets AB is defined as the uh, element-wise product AB, where A belongs to A and B belongs to B. Okay, so this is I'm talking about. So now let us be a semigroup and A belongs to S. So we are going to define our a definition like what is called as A times S. A is an element, S is the semigroup. So that is actually the meaning is um, like the product of two sets, the singleton set A and the complete set, the semigroup. Well, that is what we mean by AS without the bracket. So that is actually simple, A times small s, where S belongs to the semigroup. Likewise, we can define SCA equal to S times the singleton set A, which is actually SCA. I have SCA. Okay, SCA. Notice that AS and SA are subsets of S because A is an element of S and because it is a semigroup, so it's closed, so they are subsets of S. But generally, A does not belongs to AS or SA in general. Okay, why it is that? Because I'm giving you an example. If you take S is equal to with even integers, you having multiplication as a binary operation, it is definitely a semigroup. And also you can note that 4 belongs to this semigroup, right? And what is 4s? What is 4s? 4s is 0 plus or minus 8 plus or minus 16 is going like that. Now you can see that 4 does not belongs to 4s, right? So I have to make a change here. It is 4s. Okay, so 4 does not belongs to 4s. So uh, a when A belongs to AS, when it is that possible? If there exists a X in S such that A equal to AX. If such an X exists, then we can say that A belongs to AS. But this is possible in a certain semigroups, especially in semigroup with identity. If one belongs to S, then A belongs to AS. Why? Because for every A belongs to S, we can write A is equal to A times 1, right? Which is a which belongs to AS, right? So in a semigroup with the identity, it is always true. Otherwise, it is not. We have seen this. Now we are going to define something called S1A. Actually, we have used S1 to identify a semigroup with identity. But here, what is this S1A? It is defined as SA union A. We are going to include A in this. We have seen that in general, A does not belong to AS or SA. So we are going to define a different manner. S1A is equal to SA union singleton set A. Likewise, AS1 is equal to AS union singleton set A, and S1 AS1 is defined as SA union AS union the singleton set A union SAS. It is because SA or AS is not generally the subset of what I can say SAS. Okay, so there is some mistake. It is It is SAS. Okay, or SA or AS, not generally the subset of SAS. That's why S1A, S1 is defined like this. So these are some definitions, and next we are going to do a result which is very important, and it's a really a connection with the group theory also. If, yeah, let us be a semi-group, then the following are equivalent. Then the following are equivalent. The first thing is, so following are equivalent means you have to uh, prove from 1 to 2, 2 to 3, and 3 to 1. So this kind of cyclic method we will be used. Okay. So the first thing is that telling for every element A in S equal to S equal to SA. So not very carefully, for every element A in AS equal to S equal to SA. The second thing is very crucial one. What they're telling is there exists left identity. That's what they're telling. There exists E belongs to S for every A belongs to S, such that EA equal to A. Existence of left identity. And also existence of left inverse is they're telling. So the first thing, if you hold the first um, proposition, first what I can call what premise, then the second one can be proved from one. Okay. So existence of, actually this is left inverse. I can say left inverse. Then third is very important. If you have, if in a semi-group, if you have left identity and left inverse, then that left identity and left inverse is actually same as the right identity and the right inverse. That is, S is a group. So very beautiful theorem. We might not have studied it in our group theory classes. So this I'm telling once again, for every A belongs to S, A is equal to S equal to SA. This implies there is left identity and left inverse for every element, and that implies S is a group. Now as S a group, it will, you have to prove 3 implies 1. So this is the idea. So first we are going to prove 2 implies 3. Okay. Okay. First we are going to prove 2 implies 3. You can prove anyway, but I have just taken like this. 2 implies 3. So what I'm going to prove is the left identity is indeed the right identity, and also the left inverse is the right inverse. So what we have to assume that there exists the left identity and there exists left inverse for every element in S. So first we are going to prove that the left inverse is equal to the right inverse. So first I am taking y is equal to A inverse. This implies y square equal to A inverse multiply times A inverse, which is equal to, by using the associativity of in semigroup, A times A inverse A inverse, A times A inverse A inverse, which is equal to, we can change this one to be E. So it will be like A inverse, then A inverse is equal to A inverse, because there it is a left identity. So we have A inverse, right, which is what, y. So y square is equal to y. That means Y is an idempotent element in the semigroup. Y is an idempotent element, or Y score is equal to Y. Now we take E is equal to, using the left inverse property, Y inverse Y is equal to E, or E equal to Y inverse Y. That is Y inverse Y square, because I can replace. I have already seen that Y square equal to Y. That is Y inverse Y, Y, Y inverse Y, using the left inverse property, I have E, Y, right? That is EY is equal to Y, using the left inverse property. And what is Y? A inverse. So what I have found, the left inverse of A is equal to the right inverse also. Okay, so this is what we have found. Next we are going to prove the identity. So now we have AE is equal to, I don't know what is this, but I am just trying AE. If I can prove AE is equal to A, I am done, right? So AE is equal to A times A inverse A, because there is a existence of left inverse. But now I have, using the associative property, I can write the same thing as A inverse A. And now I have already proved that A inverse is also equal to E. That means E times A, which is A, using the left identity property. So what I have proved, AE is equal to A, which is equal to EA. That is, it is the right identity in theta. So the left inverse is the right inverse, and the left identity is the right identity. That means in a semigroup, if you can exhibit a left identity or a left inverse, it is actually a group. Okay, S is a group. Okay. Now the 3 implies 1. What is 3? We have to know what we are holding. The 3 means S is a group. I have to prove what? For every A belongs to S, A is equal to S is equal to SA. That's what I have to prove. S is a group. It will be easy. Okay. So what we are going to do is, let us fix A arbitrary in S. So I'm choosing an A arbitrarily in S, and I'm fixing that. And also I'm choosing Y belongs to S. An element, I'm choosing Y belongs to S. Then Y equal to EY, because in a group it is possible, use the identity of the group, which is equal to A inverse Y, right? Which is equal to AS. So this AS, don't worry, A inverse Y is replaced by small s. Okay, that means it is of the form AS, whereas it is an element of S. That means Y belongs to AS. Y belongs to AS. So what I have proved, I have taken Y from S, and I have proved that it belongs to AS. That means S is the subset of AS. This A is arbitrary here. Okay. Similarly, I'm taking Y equal to YE, and E is replaced by A inverse A, and I have took YA inverse as S. This one is S. Then I can prove that Y is belongs to SA also. That means S is subset of SA. So we already know that AS is subset of S. So from this includes, this means what? AS is equal to S. From this what? SA equal to S. Because we already know that SA is subset of S. And now we have S is subset of AS and SA. So what it gives you? It gives, for any element A in S, you have AS equal to S equal to SA. You have the result. Okay. So next I have to prove 1 implies 2. That means whenever you are having the property, any element A in S, A is equal to S equal to SA, you have to prove that the existence of left inverse and left identity. So we have, for every element A belongs to S, we have the property AS equal to SA. So let me choose A from S, which is SA. So in this case, you please fix A. Arbitrarily you fix A. So I mean A belongs to S, which is in fact SA using our point the one. Then there exists E, right? A belongs to SA means what? There exists E in S such that A equal to A. Here I am not mentioning this is the identity and all, just an element. There exists a E in S such that A equal to EA because A belongs to SA. I am going to prove that E is in fact the identity. Now, for any X in S, we can see that X belongs to AS. Why? Because S equal to AS. So now I am taking for any X in S, X belongs to AS because S equal to AS. That also imply what? There is a Y in S such that X equal to AY. Now this Y can be replaced by, or A can be replaced by EA, right? Then what is AY? Equal to X. Okay. So what we have done here is, I will explain once again. X belongs to S, that means X belongs to AS. So there is a Y in S such that X equal to AY, and I have replaced A using this EA. Now what I am getting? EX, because my AY is equal to X. Just note that. That's what I have previously confused. Because AY is here, AY is equal to X. So I'm replacing that AY again, X, you're getting EX. So what you have got? X equal to EX. X equal to EX means it is a left identity for every element in X. Here I am taking for every X. I got X equal to EX. So E is what? The left identity for X. Okay. That's what I have written here. There is E belongs to S. For any X belongs to S, EX equal to X. Next thing is to prove the inverse property is simple, because for every X belongs to S, E is belongs to SX. Why? Because for any for using the property for any element, we have that property Sx equal to S equal to XS. So for any X belongs to S, E belongs to Sx, which is equal to S. Then there exists X inverse in S such that E equal to X inverse X. So this is a notation, X inverse. You can call it as K or something, but our idea is what? You have to get a left inverse. So I have used this idea, X inverse X. Hence the result. So you can go back and understand once again this proof. It is a little tricky, but not difficult. Okay, so that is the result. So this result is very crucial. We will be using this in the coming results and observations and propositions. So next thing is we are going to define what is called a zero group. A semigroup with zero element is called a zero group if S difference the set singleton set zero is a group. That means a zero group is nothing but a group is adjoined a zero element. If you adjoin a zero element to a group, we have already seen that it will not remain as a group, right? In the previous lecture. So such groups exist. So if a semigroup is equal to G union 0, then we will call that is a zero group. That semigroup can be called zero group. Now we have a proposition. A semigroup with zero is a zero group if and only if for every A belongs to S different 0, AS equal to S equal to SA. So this is the idea. So if a semigroup with zero is a zero group, this implies this property, and if you have that property, that semigroup is a zero group, or what I can say, S different 0 is a group. You can prove that. So first I am considering if S is a zero group, whether we can show this property. So if S is a zero group, then we know G is a group, and we have, for a group, I have proved in the previous section, the first section tells me that AG equal to G equal to GA, right? If S is a group, we have this property. For every A belongs to G, G is nothing but S difference 0, right? So now the necessary part will follow easily, because if we calculate AS, it is nothing but what? AG union 0, which is equal to AG is G from this. So this is G union 0, which is nothing but S. SA is equal to GA union 0, G union 0, which is S. That is AS equal to S equal to SA. So if it is a zero group, this property will hold easily. Now we have to prove the converse. Conversely, assume that S has the given property. So consider this set G, which is S difference 0, which is a subset of S, definitely. Is this non-empty? Yes, of course it is non-empty, because a semigroup with zero element has at least two members. We have already mentioned it properly in the previous lectures. So because of that, even if you avoid zero from that, you can find at least one element. That means G is non-empty. Since a semigroup, yeah, at least two elements. Now, what is my claim? I claim that G is closed under binary operation. I have to prove that G is a group. I am now considering the subset S difference 0. I have to prove that G is a group while holding the property. So how do I prove G is closed under binary operation? It's very simple. Let us take AB belongs to G. Of course, G is a subset of S. And suppose that AB is not belongs to G. If AB is not belongs to G, the only possibility is AB belongs to the singleton set 0. That definitely will imply AB equal to 0. Because S is a semigroup, it is closed under the binary operation. Now we calculate S square. What is S square? S times S. So S can be replaced by SCA, because using the property in our hand, this is possible, right? S equal to SA. Why it is possible? The A is coming from where? G. A is from S difference 0. So S equal to SA. The second S can be replaced by BS. Now using the associative property, you can verify it very clearly. I'm not going to do this. It is actually true. So in the associative property, you can write S ABS. AB is 0, right? AB is 0. That means it is singleton set 0. So S square is singleton set 0. Okay, if the closure property does not satisfied, what we are getting S square equal to 0. What is the problem? Now S equal to AS, which is a subset of S square, which is singleton set 0. That means what? S is equal to singleton set 0, which is impossible because S has at least 2 elements because it is a 0 semigroup, right? Semigroup with a 0. So that is a contradiction. So our assumption is wrong. Closure property is holding. That means AB belongs to G. We got to the contradiction because we have assumed that AB does not belong to G. Okay. So a closure property has satisfied. Now you have to observe a little. Also by the given property, what is the given property? AS equal to S equal to SA for any A. So I am taking A and B belongs to G, then I will get X and Y in S such that AX equal to B and YA equal to B. How do I get this? This is very simple because using the property, what is the property? For any A belongs to S, I have AS equal to S equal to SCA. What I'm going to do, I'm choosing element from B from S. Then B belongs to AS. So B must be of the form A into X, right? That's what I have used here. Similarly, it is also belongs to SCA. So it is of the form some YA, right? That is I am using here. It's very easy, right? So using the given property, I will get two numbers. XY belongs to S such that AX equal to B and YA equal to B. Very easy. Now we can look at this case. My A and B are from G. What is G? S difference 0. Then X, Y cannot be 0. If X and Y are 0, what happens? B is 0. But B is not 0, right? That's what I'm telling. A and B belongs to G. B is non-zero element. So if I will have X and Y are 0, if either one of them is 0, then I will get B is 0, which is impossible. That means X and Y are from where? Actually, X and Y are non-zero. That is, X and Y are from G. This will imply, in return, what it will imply? AG equal to G equal to GA, which is a property of a group. We have already seen that if a semigroup or satisfies this condition, it will be a group. Okay. So that is the idea. So we have proved the theorem. So this is a very good theorem, which again I will tell you, if S is a semigroup with a 0, it's a 0 group if and only if for every element A belongs to S difference 0, we have the property AS equal to S equal to SCA. Okay. Now we are going to define what is called subsemigroup. A subsemigroup is a subset of S, which is a non-empty, and it is said to be the subsemigroup if T is closed under the binary operation hours. We don't want anything else. It's just closed under the binary operation. And associativity will definitely follow. What are the examples? The very proper examples for any semigroup would be the complete set semigroup S, singleton set 0, single 0. If it has 0 element, then the 0 element is a subsemigroup because 0 square Any powers of 0 will be 0. Same like E1 identity, if semigroup with the identity, then identity singleton set will be the subsemigroup because any power of 1 would be 1. Now this is very nice. If you have an idempotent element in a semigroup, then what is idempotent element? E square is equal to E. So for that fellow also, any power of E would be belongs to what in the any power will be E itself. So that's also a semigroup. So these are the four worthy mentioning semigroups. And for another example, I am having, if you look at the integers using addition, it's actually a group. Anyway, this is a n plus is not a subgroup, but it is a subsemigroup of that particular semigroup. Now, like group theory, we will also consider subgroups of semigroups. So, I mean, groups can be seen as okay, it can be embedded into semigroups, right? So, if T is non-empty and T is a subset of S, it's a subgroup if you have this property. For every A belongs to T, A T equal to T A equal to T. Okay, if it's a subgroup, if you have that property. But this it is very simple to prove that it is closed under binary operation because if it is for any A belongs to T, A T equal to T. That means what? T square definitely would be the subset of T. Then if this property holds, we say that T is a subgroup. Okay. Yeah. Now, what are the examples? If 2Z plus is a subgroup of Z plus, 2Z using the binary operations multiplication is a sub-semigroup of Z multiplication. It's a sub-semigroup because 2Z multiplication is not a subgroup because inverse does not exist. Also, Z multiplication is also not a group. Okay, so these are different type of examples. The R star or R difference 0 using multiplication is a subgroup of a proper semigroup, R multiplication. So these are the examples of subgroups and subsemigroups. This definition is very clear using our already proven theorem because if T is closed and if T is closed under the boundary operation, that means T is a semigroup, and a semigroup satisfying this condition is a group. So from there we have the motivation to define the subgroup. Okay, so that is the idea about this. In the coming lectures, we will study about homomorphisms and isomorphisms, direct product, and many more things. So thank you for this attention. Please go through the lecture. Even if you have doubt, you can ask in the comments. Okay, thank you.